Assalamualaikum and have a nice day everyone. I'm Najwa and my partner Jason will present our analog assignment. So I will explain about the full wave rectifier with capacitor filter. The main function of full wave rectifier is to convert an AC to DC. As the name implies, this rectifier rectifies both the half cycles of the input AC signal, but the DC signal acquired at the output still have some wave. To decrease this wave at the output, this filter is used. In the full wave rectifier circuit, using a capacitor filter, the capacitor is located across the RL load resistor. The working of this rectifier is almost the same as a half-wave rectifier. The only dissimilarity is half-wave rectifier has only one half cycles, positive or negative, whereas in full-wave rectifier has two cycles, positive and negative. Once the AC voltage is applied throughout the positive half cycle, then the diode D1 gets forward bias and permits flow of current, while the D2 diode gets reverse bias and blocks the flow of current. Throughout the above half cycle, the current in the D1 diode gets the filter and energizes the capacitor. But the capacitor charging will only occur just when the voltage which is applied is superior to the capacitor voltage. Firstly, capacitor will not charge as no voltage will stay among the capacitor plates. So when the voltage is switched on, then the capacitor will get charged immediately. Throughout this transmission time, the capacitor gets charged to the highest value of the input voltage supply. The capacitor includes a highest charge at the quarter waveform in the positive half cycle. At this end, the voltage supply is equivalent to the voltage of the capacitor. Once the AC voltage begins falling and turns into less than the voltage of the capacitor, after that, the capacitor begins discharging gradually. As the input AC voltage supply gets the negative half cycle, then the D1 diode gets reverse bias, but the D2 diode is forward bias. Throughout the negative half cycle, the flow of current in the second diode gets the filter to charge the capacitor. But the capacitor charging occurs simply while the applied AC voltage is superior to the voltage of the capacitor. The capacitor in the circuit is not charged fully, so the charging of this doesn't occur instantly. Once the voltage supply becomes superior to the voltage of the capacitor gets charging. In both half cycles, the flow of current will be in the similar direction across the RL load resistor. For Zener diode connection and waveform, Jason will proceed.
Okay, thank you Najwa for that presentation. The connection of the Zener diode acts as a voltage regulator. A complete and stabilized power can be obtained by using the rectifier diodes to change the AC power to DC power. The rectified voltage is filtered to reduce the ripple on the rectified waveform. A Zener diode is then used to regulate the voltage to its desired final value. Okay, moving on to the waveforms. The first waveform steps down the high voltage AC mains to low voltage AC. Okay, so the step down is basically showing from the transformer as it steps down from higher AC supply. And as for the waveform, if we go to the graph here, you can see the waveform. This is the first waveform from the step down high voltage AC to the low voltage AC. As you can see over here, the voltage goes up to around 125 and the current goes slightly higher than 750 milli. Okay, then we have waveform 2, which converts the AC to DC, but the DC output has a large ripple component. So this the rectifier, so it converts the AC to DC. So as for the waveform for that, and as you can see the waveform here, which is much smaller. The blue line waving oscillating form here is the waveform for which converts the AC to DC. This is with the DC output which has a large ripple. Then next would be smooth the DC from varying greatly and reduces the ripple component. As you can see on the waveform, the ripple has shortened, making it smaller, hence making it more smoother. As you could have seen from the previous waveform, the ripple is much more larger, whereas this is slightly smaller. As for the fourth waveform, it eliminates a ripple by setting the DC output to a fixed voltage. And as you can see from this waveform here, it's much more smoother. The pink line is our graph. As you can see, it's much more smoother. It has smoothened out tremendously. However, it still has a minor ripple to it, which is not so visible here. As we go to waveform 5, it is the part of the circuit to which the DC power is delivered to perform useful operation. Looking at the graph, it might not be so clear to see it, but then if you look in the center here, right here, where the cursor is, this gray straight line is the final waveform of the DC output. And as you can see here, it is much more smoother compared to the previous waveform 4. It was pink and there was a minor ripple which was slightly above the x-axis, which you can do a comparison here. Now you can see more clearly the pink line is waveform 4 and the gray line is waveform 5, which the pink line has a slight ripple and the gray line is much more smoother and given our final DC output. Thank you very much. I hope you enjoyed this presentation. Please stay safe and I hope you enjoyed this presentation. Thank you.